Hello, my name is Kishan Agarwal. I am from CSE Section B. Today I am presenting my tech talk of Basic Electrical Engineering, and my topic is Thermoplastic application for pulse power alternators. So let's begin. The field coil is the primary component of the rotator assembly that provides the rotating magnetic field for the pulse power alternator. The design of the field coil is optimized so that it will produce the required magnetic field with minimum transient losses. The high current required to produce the current amp turns along with the mechanical loads due to high rotational speeds presents further design requirements for selection of field coil material, insulation and surrounding material that completes the matrix of the field coil subassembly. With the addition of active coiling requirement in the field coil design, surrounding materials must be selected that retain electrically insulative properties and are thermally conductive to allow sufficient heat removal from the field coil. Thermoplastics are now being revived to replace traditional glass epoxy potting compounds that are thermosetting plastics that have been used extensively in pulsed alternator designs. Filters can be added to tailor properties of the thermoplastic, such as ceramics to increase thermal conductivity at the cost of an increase in density. Thermal analyses have been performed that show the benefits of using thermally conductive potting compounds. In addition, subscale field coil mock-up mortars have been encapsulated and tested to demonstrate encapsulation of current field coil geometry. So this is a basic pulse power alternator. So current requirements for pulse power alternator design have dedicated the need for continuous discharge over an infinite period of time or steady state operations. The primary limiting factor for achieving such a design requirement has been thermal management of losses from ohmic heating and windage. The most direct method of managing such losses is the placement of cooling tubes within the winding of the armature and field coil conductors. Although this method sounds simple and straightforward, additional design issues arises when incorporating cooling tubes inside the field coil conductors. The field coil is typically located in the rotator between composite bandings, spinning at high speed for maximum energy density. High voltage potential also develops the field coil during discharge, as the correct amount of amp turns must be achieved to generate the required magnetic field or flux. Due to this high voltage potential, designs that feature intimate contact between the cooling tubes and the field coil require as well insulation breaks within the circuit to isolate the field coil electrically from the shaft and exterior auxiliaries at ground potential. The isolation break would need to withstand the high stresses from rotational loads within the rotor structure and the high internal fluid pressure generated from these same rotational loads. The additional design complexities created by the intimate contact cooling design have led to the placement of current field coil cooling systems away from the conductors. The benefits of these designs are the freedom to design the cooling path independent of the field coil geometry and the inherent electrical isolation achieved by the no intimate contact between the cooling tubes and the conductors. The problem that remains is sufficiently removing the heat generated from the field coil and windage losses through the insulation, glass and graphite materials, which generally have low thermal conductivities. In previous designs, the field coil conductors were wrapped within a thin layer of insulation and a thicker layer of glass cloth that was then potted with an epoxy resin through a vacuum-assisted resin transfer mechanism, that is VARTM process. In general, the thermal conductivity of such materials is equivalent to 0.2 to 0.3 watt meters Kelvin. New materials with increased thermal conductivity but which are still electrically insulative will improve heat transfer for current field coil cooling designs. Over recent years, work has been performed in developing thermally conductive thermal plastic for commercial use. Ceramic filled thermoplastic have been used in spindle motors for the disc drivers, where design seek to optimize cost, efficiency, and size. The fillers allow physical properties such as modulus, strain to failure, and conductivity to be tailored to the desired application. These materials have also been used in high-strain applications that better reflect the size and load requirement for pulse power generators. The stator winding of a submersible electrical motor were encapsulated, which was required to withstand external pressure of 10,000 psi at depth up to 20,000 feet. Now, we'll discuss the thermal performance comparison of pulse power generator. Thermal FEA models and simulations have been performed to study the benefits of using thermally conductive thermal plastic for pulse power alternators. One design configuration was analyzed to compare the performance of the traditional epoxy glass system to that of encapsulated field coil. In this design configuration, the cooling tube assembly was located in a layer below the field coil structure. Thermal loads were generated from the windage heating on the outer banding and from field coil losses modeled as repetitive pulse loads. For the first case, the glass epoxy was modeled with a thermal conductivity of 0.3 watt meters Kelvin, while the second case modules a resin formulation produced by LNP Engineering Plastics Inc. conduit, which has a conductivity of 1.4. From the results shown in figure 1, the increased thermal conductivity decreases the temperature of the field coil and outer banding, which impose limits on operating temperatures. The thermoplastic greatly increased the number of discharges allowed before any material reach. So here, in these graphs, comparative thermal performance of baseline for epoxy glass system versus thermally conductive thermal plastic. So we can see the difference in outer banding ID and outer banding OD and field coil conductors in both the graphs. Now, manufacturing applications. In addition to the thermal benefits provided by thermally conductive thermal plastics, many manufacturing benefits are also present. The current porting procedure for epoxy glass field coil matrix requires a labor-intensive glass wrapping processes of the field coil conductors and an extensive VARTM procedure to produce a single coil. A minimum of a week of effort is required in setting up the VARTM system, and the process of filling wrapped coil with epoxy can take a day. In contrast, overmolding a structure with thermal plastic takes about a minute. This process can now be industrialized and would allow multiple field coils to be encapsulated in a single day. Injection molding of thermal plastics decreases the chance for formation of voids such as those that develop during a VARTM. Due to the high temperatures and pressures, the thermoplastic fills the mold. The major impediment to developing the technology for injection molding larger field coils is the cost inherent in the mold construction. Large molds require and must have a sophisticated system of retraceable pins to hold and release the coils during filling, with heated runners to transport the molten thermal plastic through the mold to the cavity. In addition, thermoplastics are inherently more viscous and require significantly higher pressures to fill the mold. Thus, a very expensive, high-strength mold is required that is capable of sustaining in internal pressure in excess of 5 psi. There are only a limited number of injection molding machines in the country with the tonnages required to encapsulate parts of the size of a field coil. In order to prove out the technology and applications to current field coil geometry designs and insulation systems, small flat coil mock-ups, that is, mini coils, were manufactured and encapsulated with various insulation wraps and thermal plastics. The mini coils maintain the same conductor height and spacing as the current field coil designs with an approximated conductor aspect ratio. The goal of these trials was to demonstrate the ability to encapsulate field coil geometries with the thermally conductive thermal plastic and to evaluate the compatibility of the primary insulation layers with the process. The thermal plastic enters the mold at 310 degrees Celsius and pressure of 35 to 55 megapascals, that is 5 to 8 ksi. The primary layer of insulation or the field coil conductors must withstand these processes. 9 mini coils were produced for thermoplastic encapsulation trials. 4 coils were wrapped with 3 half-lap wires of etched Teflon PTFE, which produces a final insulation build-up of 0.3 mm. The next 4 coils were wrapped with 3 half-lap wraps of Kapton CR, which produces an insulation build-up of 0.15 millimeters. The last coil was first coated with 0.1 millimeters of Durafilm 300 polyimide resin and then overwrapped with 2 half-lap wraps of Teflon for a total insulation build-up of 0.3 millimeters. As shown in the figure 2, it is showing a mini coil wrapped with Kapton CR. Flat mini coil wrapped with 3 half-lap wraps of Kapton CR film is shown in the figure. The leading candidate material for the thermoplastic encapsulation was a thermally conductive nylon 4,6 based resin manufactured by L&P Plastics. Conduit, this is the company name. Nylon 4,6 based resins were chosen for their ability to retain properties better at elevated temperature, and these particular resins provided a conductivity of 1.4 watts, 5 times better than the current glass epoxy systems. A backup resin was also selected, Conduit PTF 2155, which is a nylon 6 based resin with a conductivity of 0.5. So after the beginning of the trials, complications developed as the high conductive PDX resin formulation was implemented. Resin cracks developed during cooling down of molded part. These cracks were attributed to the high filter content that gives the resin high thermal conductivity, but also lowers elongation and makes the resin more brittle. The testing then switched to the backup resin. which successfully encapsulated the remaining mini coils. An encapsulated mini coil as shown in the figure 3. So this is a mini coil, encapsulated coil sliced for visual evaluation. By using thermoplastics, it becomes easier for the pulse power generator for the insulation purpose. So the encapsulated coils were evaluated by high-pot testing and visual inspection of sliced samples under a microscope. Sections of mini coils were sliced and polished to look for voids present in the fill and for visible damage to the field coil insulation. This figure 4 shows the insulation detail of a Kapton CR wrapped coil, and figure 5 shows that a Teflon wrapped coil. Kapton CR layer after injection, and this is Teflon wrapped layers after injection molding. So now, visual inspection of sliced coil did not show any evidence of void formation throughout the encapsulant. There also did not appear to be any evidence of damage to the insulation layers, except on some exterior layers of Teflon film where deformation occurred. An additional observation was the formation of a boundary layer in the encapsulation filler on the Kapton wrapped layers that is not present on the Teflon wrapped layers. A close-up of these layers is shown in the figure 7. DC high potting of the encapsulated mini coils to a ground plane demonstrated hold-off strength of 22 to 30 kilovolts, well in excess of designed filled coil voltage levels. So this is the deformation of exterior Teflon layer, and this is close-up of encapsulated Kapton wrapped conductor. Thin boundary layer of nylon appears to have a different grain structure adjacent to Kapton insulation layers. There is a picture and a microscope. Results from thermal analysis shows the benefits of using thermally conductive thermoplastics to enhance rotor cooling for pulse power alternators. In addition to thermal performance, it also introduces industrialized manufacturing processes that can greatly reduce time and cost for mass production. More work is needed to determine the achievable limits of resin content and thermal conductivity that can be achieved with conventional thermoplastic injection molding equipment and meet the rigorous pulsed alternator field coil designs. So using thermoplastic, we have seen that using thermoplastics, they can be manufactured many different kinds of pulse power generators or pulse power alternators, which give much better thermal performance and greatly reduce the time and cost of production. So thank you.